In this video, we're going to learn about the information we can get using our derivatives. So when we were finding our max and mins, we were talking about critical points. And the critical points are the points on the graph where the derivative or the slope is either 0 or undefined. So when I see relative max or mins, my derivative here would be 0, right here, and right here. We can have what we call inflection points, so where it looks kind of flat, it's changing direction. If we have any holes or breaks, this derivative would be undefined right here. If I have an asymptote, again, the graph isn't continuous, so it would be undefined. If I have any vertical tangents, which is also sometimes called an inflection point, and any sharp corners or cusps. These are all the places that we would have a 0 or an undefined slope. So using that information, I can look at a graph, just like we did in the last video, and figure out where are my extrema. So if I'm looking at a graph, remember we have absolute mins, absolute max, and then we can have relative or local max and mins. So I have an absolute max looking at this curve at the highest point right here, which is at the point 5, f of 5, which in this case is a 7. So there's my absolute max. Then I look and I say, okay, I have an absolute lowest point over here. So that's my absolute min, is at -4, f of -4. But now is where I have to pay a little bit more attention. So extrema are maxes and mins. Where the graph is 0, where it's undefined, is where I'm going to get those critical points, but I just want max and min. So right here I have a local max, a local min. It's a low value at 0, f of 0. And then this we can think about as an extrema because something is happening there, but it's not really a max or a min because the graph wouldn't be defined there. The derivative is not defined. And then I have my two endpoints, but they don't match anything else. So we just have an absolute max, an absolute min, and one local minimum on this. Now, we do have something happening. -2, f of -2 is still a critical point, but it's not an extrema. Okay, so this time we're given the function f of x equals x minus 1 squared plus 6. We want to find all local extrema, find the absolute extrema on the interval -3 to 3, and then we want to sketch a graph of what f prime of x would look like. Okay, so if I want to find extrema, I know I have to find my derivative. So f prime of x is equal to 2 times x minus 1 times 1 using my chain rule plus 0, derivative of 6. So I can clean this up a little bit. So f prime of x is equal to 2 times x minus 1. And I want to know when the derivative is equal to 0. So when 0 equals 2x minus 1. So I know that happens when x equals 1. This is never undefined, so I'm not going to have an undefined area to look at. So now the values I need to find to know if I have absolute or local max and mins is I need to find f of -3, I need to find f of +3, and I need to find f of 1. Okay, so when I plug in my -3, I end up getting out a 22. When I plug in +3, I'm going to get a 10. When I plug in my +1, I get a 6. So I'm looking at these outputs, these y values, to see which is the highest, which is the lowest. So my highest value here is the 22, so this is my absolute max. The 6 is the lowest of all of these, so this is an absolute minimum. And it's absolute in this interval because of that. So I know this is a local extrema, so it's definitely a minimum in comparison to the graph. In the interval that we're looking at, we know that it's an absolute. And then the last part said, go ahead and sketch f prime of x. Well, this tells me that f prime of x is equal to 0 when x equals 1. And then I need to know what else is happening to the graph. What's happening when x is 2 or 3 or -1 or -2? So we have to kind of think about what the graph looks like. So I'm going to actually sketch this parent graph. This is a quadratic. It got shifted to the right 1, and then it went up 6. And so this is roughly what that graph is looking like. And when I want to graph my derivative, I can say, well, right here, all of these slopes are negative, going up to 0, and then all of these slopes are going in a positive direction. So this is what it would look like, right? And I'm essentially graphing the line 2x minus 1, which tells me this one right here would be at the point -2. Now we can do the same thing and find the same information using our first derivative test. So here I have my graph of f of x, and if I wanted to graph its derivative, I would be looking at the slopes. So we'd say, well, the derivative is 0 right there because that's a max or a min. This is a max or a min, so I have a 0 there. The slopes are increasing here, right? These are positive directions, so my slope has to be up here. These are decreasing, so it's negative. These are increasing, so it's positive. So my first derivative test tells me if I'm looking at this and my derivative, so down here this graph is f prime of x, if my derivative is switching from a positive to a negative, this point is corresponding to this, gave me a max. That's what this first one tells me. The second one says if it's changing from a negative down here to a positive, I'm getting a minimum. And that's what this one is telling me. So it's working for us. So the way we can use this if we don't have a graph is we're going to find all of those critical numbers, find where the derivative is equal to 0 because that's specific for this, or when it's undefined, and then you check numbers to the left and the right. So showing you with this, if I draw kind of just a number line for f prime of x, I say, okay, I know that the critical values were at when x is 1 and when x is 2. So then what I need to do is I need to find out what would be the values of f prime of x between these. So notice there are 3 regions here that we have. We have this region less than 1, we have this region greater than 2, and then you have this region in between. And we want to know if they're positive or negative. Well, the slopes over here we said are positive. The slopes between 1 and 2 are decreasing, so they are negative slopes. And then the graph was increasing, so these were positive slopes. So switching from a positive to a negative told me I had a max. And from a negative to a positive, it gives me a min. Okay, so for this one we're given f of x equals x squared minus x plus 4 over x minus 1. So the first thing we want to do is find our critical values. So we want to know what is our derivative, and we want to know when does it equal 0 or when is it undefined. Well, I know that this function is undefined at x equals 1, so that's one of my critical values. To find the rest, I need to know when that numerator is going to be equal to 0. Those are going to be my critical values. So I'm going to find my derivative, f prime of x, so that's low, times the derivative of the top, minus the top, times the derivative of the bottom, all over the denominator squared. I'm going to clean this up just a little bit. So f prime of x, if I distribute, I have 2x squared, minus x minus 2x is minus 3x, plus 1, minus x squared, plus x minus 4, all over my x minus 1 squared. And I know it's undefined when x equals 1. We already got that. So we want to know where this is equal to 0. So if this is equaling to 0, I don't care what's in the denominator, I care about that numerator. So I'm going to set this equal to 0, and just for space, I'm going to condense it now. 2x squared minus x squared is x squared. Negative 3x plus x is minus 2x. Positive 1 and negative 4 is negative 3. And I can solve this by factoring. It factors to x minus 3, x plus 1. So I have x equals 3 and x equals negative 1 are my critical values. So I have 3 critical values. X equals 3, x equals negative 1, and x equals 1. So to figure out where my intervals are increasing or decreasing, I want to know if those are max or mins. So I draw a first derivative number line. So here's f prime of x, and the values I need to mark are negative 1, 1, and 3. And I want to know what's happening to my slope. Is it increasing or decreasing? Well, if the slope is positive, the graph would be increasing. If the slope is negative, the graph would be decreasing. So I can figure that out by plugging in values within each region. So I'm going to try f prime of -2. Well, if I plug in -2 squared is 4. -2 times -2 is +4, so 4 plus 4 is 8. 8 minus 3 is 5. So in this region, I know my graph is positive. Right? I plugged in a -2. Then I'm going to check something in between. So between -1 and 1, let's try 0. So I'm finding f prime of 0. So 0 squared minus 2 times 0 minus 3 is -3. So I know it's negative here. Between 1 and 3, I'm going to try 2. So I want to know f prime of 2. So 2 squared is 4. 2 times -2 is -4. So 4 minus 4 is 0. And that's -3. And then I need something greater than 3. So I'm going to plug in 4. So I'm going to find f prime of 4. 4 squared is 16. 2 times 4 is 8. 16 minus 8 is 8. 8 minus 3 is 5. So this is positive. So here I can see the graph is increasing. And this is where I'm going to run out of room right now. Let me grab a new page. Okay, so using our derivative line over here, we can say that the graph is increasing on the interval from -infinity to -1, and it's also increasing from 3 to infinity. It's a really bad infinity sign, it looks more like an 8. It's decreasing where the derivative is negative, so it's decreasing from -1 to 1, and then it's decreasing again from 1 to 3, but exactly at 1, we know that that derivative is undefined, so I can't say it's increasing or decreasing exactly at 1. Next, it asked for my local and relative extrema. So I know when the derivative changes from positive to negative, I have a relative max. So I have a relative max when x equals -1, and I have a relative min when x equals 3, when it changes from negative to positive. Now to find my maximums, my absolute max on the interval from 0 to 4, I need to plug all of those in. So in order to find absolute max, I need to find what is f of -1, and then I also need to know what's happening at my endpoints. What's happening at f of 0, and what's happening at f of 4. And again, I need to plug those in to the original to get those values. Okay, so after doing calculations, I plugged in f of -1, I find that it equals -3. When I plug in 0, I find I get -4. When I plug in +4, I get 16 over 3. So here I can see that my relative max is 16 over 3 at the endpoint f of 4. So in this case, because it's on the interval, that's my absolute max. And that's greater than what I got when I plugged in the -1. So the absolute max is when x equals 4. My absolute minimum, -4 is the lowest I got. If I plug in my 3, because I need to verify that one, right? I didn't look at f of 3. When I plug in my f of 3, 3 squared is 9, 9 minus 3 is 6, 6 plus 4 is 10, 10 over 2 would give me a 5. So that, even though we know x equals 3 is a relative min, that is not my absolute min. So my absolute min is when x equals 0. Okay, so in that last example, at the point 1, we had nothing going on. It went from a negative slope to even still negative slope, but we know the derivative was undefined. It was a critical point. What else could that be telling me? So think about a ski slope. So when you're skiing, right, you start at the top of the hill. I start up here, and I go a little bit slow, and then my speed builds up, builds up, builds up, and then as I get to the bottom, it slows down, it slows down, it slows down. So it's the steepest right here at what we call an inflection point. Okay, and what that's doing is it's showing me how the curve bends at a certain point. So up here at the top, it's kind of bending down. It wouldn't really hold water if I poured water on it, but down at the bottom, it starts bending up. And this is what we call concavity. It's telling us how things are changing. So if f prime of x is decreasing, right? If it's getting smaller and smaller and smaller, more and more negative, right? And here it's a negative slope, it's getting more and more negative. We know that it is concave down. And if f prime of x is increasing, getting bigger and bigger and bigger, we know that that the function is concave up. All right, and I always remember that as a decreasing slope, it's going down, concave down. Okay, and here again, to help you remember, I call what's called the ruler trick. So a concave support ruler, curved support, if it's concave down, then my ruler is going to sit on top of it. If it's concave up, the ruler is going to sit under it. So right here, my slope is a negative slope, but it's getting less and less negative. It's approaching 0, and then it's getting more and more positive. So this is what we mean in this direction. F prime of x is increasing. It's going from a negative number to a positive number. It's an increasing slope. And then here, so we have right at this point, it's changing. It's a positive slope, but it's the most positive it's getting, and then it's going back down to a slope of 0. Now, at that point S, it's hard to tell because we're going from a positive to still a positive. So this is where we're going to start changing, and we can look at what we call the second derivative test to see what's happening right there. So the second derivative can tell us a lot of information. So if f is a twice differentiable function at some value c such that f prime of c equals 0, so the first derivative equals 0, then we can figure out if we have a relative max or a min. We can also determine the concavity. So if f prime of x is greater than 0, then f of c has to be a minimum. And we also know that when f double prime of x, get my pen back, if that second derivative is greater than 0, we know that it's concave up. And if that second derivative is less than 0, then that c value has to be a minimum. And it tells me that if it's a negative, it's concave down. So we can use the second derivative test to help classify critical points of a function. So we have h of x equals 3x to the fifth minus 5x to the third plus 3. So I can find h prime of x. Using my power rule, I get 15x to the fourth minus 15x squared. And then I'm going to find h double prime of x. So this is 60x to the third minus 30x. Now I want to know where it's greater than 0 and less than 0. If the second derivative is equal to 0, it depends on what's happening with the first derivative. So I'm still going to set my second derivative equal to 0. I'm going to factor out my 30x. So then I'm left with 2x squared minus 1. So I have x equals 0. And I have x equals plus or minus the square root of 2 over 2. So now that I know where that second derivative is equal to 0, I'm going to make a second derivative number line, f double prime, and I'm going to mark those values. So I know it's at 0, at radical 2 over 2, at negative radical 2 over 2. And first thing I'm going to work on is my concavity. So I want to know, is this second derivative positive or negative? Well, I know where it's equal to 0, so I need to look at these regions in between where it's 0 to find out if it's increasing or decreasing. So radical 2 over 2 is approximately 0.701, so I can check negative 1/2, I can check positive 1/2, I can check positive 1, and I can check negative 1. So if I plug in negative 1 to the third is still negative 1, so that's negative 60. Negative 30 times a negative 1 would be a positive 30, so negative 60 minus 30, in this region it's negative. I'm going to check in negative 1/2. Negative 1/2 to the third is going to be negative 1/8, so I have 60 over negative 8. And then I have negative 30 times negative 1/2, so that's going to be a positive 15. So 60 over 8 minus 15 over 8 turns out to be a positive. When I check my positive 1/2, 1/2 to the third is 1/8, so I have 60 over 8 minus 15. This is going to be a negative. And then I try my positive 1. 60 minus 30 is 30, so that becomes positive. So we know that this graph is concave up on the interval from negative radical 2 to 2 over 2 up to 0. and then from radical 2 over 2 to infinity. It's concave down where it's negative. So from negative infinity to negative radical 2 over 2, and from 0 to radical 2 over 2. Now to figure out if I have max or mins, I need to know for my derivative what are those exact values. So I need to know when h prime of x is equal to 0. So I'm going to set this equal to 0. I can factor out a 15x squared. So I'm left with x squared minus 1. When I solve, I have x equals 0, x equals plus or minus 1. So now I'm still going to use that second derivative test to help me out. And I said, okay, when x is 0, my second derivative at that value, because f double prime is positive, we want to know what's happening. Well, because the second derivative is 0 at both, that doesn't tell me enough information. But at positive 1 over here, my first derivative is positive. This tells me that at x equals 1, I have a relative minimum. Right, they're backwards on this one. And then I did my work. I checked negative 1 into my second derivative. So that tells me when x equals negative 1, because my second derivative is negative, this is a relative maximum.